After having seen the different aspects of H.323, in this lecture we are going to study about the multiplexing schemes in H.323. Now, one trade-off aspect which we have been discussing, I think we discussed over the past few classes, sometimes we are referring to this. See, there is a trade-off that one has to do when the H.323 is being used, and that is between the efficiency of compression, or rather to say it is a trade-off between the bit rate and the efficiency that we are having in terms of its payload transmission. You see, one of the aspects that we do in the case of H.323 is that we I mean normally try to use a codec which is having a very low bandwidth codec. So, that if you are taking something like a 8 kilobits per second codec, in that case in order to accumulate an audio frame, okay, you may have to take substantial amount of time. But when an audio frame is accumulated, then what you can do is to transmit that audio frame over the IP, or rather to say you have to packetize that audio frame, and what you do is that by introducing some headers, okay, you have a scheme so that the header is followed by the payload, and normally for VoIP applications what we encounter is that the payload size becomes often quite small, because if we try to make the payload on the higher side, okay, in that case the difficulty that we face is the larger accumulation delay in order to form that particular audio frame. Okay. So, it is something like this, that supposing this is the header information, okay, which is more or less a fixed information for a VoIP packet. Say this is the composition of a VoIP packet we are talking of, and this is the header and this is the payload. Okay. Now, normally as a payload we consider one audio frame, and obviously a small bit rate would mean a large accumulation time. So, what is the solution? Either we have to go in for a larger bit rate, or otherwise we have to accept this accumulation time, okay, which will lead to delay, because this, as you know, this buffering delay is also forming a very considerable part, because as we discussed that in the standards of H.323 it is specified that the maximum end to end delay, barring the very long distance calls like what happens over the continents, okay, I mean all the overseas communication, there we may have to tolerate end to end delays which is higher than 150 milliseconds, but normally in 150 milliseconds of total end to end delay time if we take, in that case this payload formation itself will take a very significant part of it. Okay. And not only that, now in order to reduce this problem, what we said is that we reduce the payload size, but of course the fragmentation we do not do in less than one audio frame. Say one audio frame is the unit which we consider, and even then it is seen that whereas whereas one audio frame in a very compressed form could mean that it is 10 to 30 bytes, the payload the header of the VoIP packet typically becomes 40 bytes. So, you can see that what is the payload efficiency? The payload efficiency is very small, because if it is forming only let us say 10 bytes, I mean take the worst case, if it forms 10 bytes out of total 10 plus 40, that is 50 bytes of information, only 10 bytes is the payload, in that case it is an efficiency of only 0.2. Okay. So, naturally we have to think about increasing this efficiency and how we can do that. One of the schemes whereby we can do it is to introduce a kind of multiplexing scheme between various VoIP sources who would like to send their packets to the destination. Now, normally in a large scale VoIP application, it is not just one user who would like to send the VoIP packets, but there would be several users. Okay. So, if we can introduce a multiplexing scheme whereby we can transmit more than several audio frames. Okay. I mean if we transmit several audio frames which are coming from different sources, okay, and multiplex them together, okay, perhaps in that case it should be possible to send large information, and we have to see that in such a kind of scheme is it possible to really have some amount of compression in the header information. Okay. So, this is what is being done as a multiplexing scheme. So, typically what we are going to have is something like this, that at the source end we are going to have a multiplexer, okay, and supposing the multiplexer is connected to different sources. Okay. So, let us say that we draw some sources. Okay. Now, each source is lying on its own local area network. Okay. Supposing we have a local area network, okay, through which we are sending one audio packet. So, when we are sending the audio packet, then that audio packet will contain a header information and then there will be a payload. Now, when we are sending the audio packet, essentially what we are doing is that, I mean this is itself a LAN. So, that is why we have to send it not only over the RTP. So, typically the essential ingredients that would compose the this bit stream is that there will be UDP header, or rather to say there will be to start with there will be IP header, there will be UDP header, there will be RTP header, and then there will be payload information. Okay. So, this whole thing IP, UDP, RTP headers plus payload, okay, this would be the composition of this entire packet. Now, out of this say header is this much and the payload is this. In fact, here we can we may have a bad efficiency in the sense that as I was telling you that since the unit here, I mean since the payload is only one audio frame. So, that is why we can say that one audio frame will be a fraction of what the total bit stream is. So, here the efficiency is low, but nevertheless in this case we may not mind having a poorer efficiency, because the bandwidth what we are having here, I mean for the local area network normally there is no bandwidth constraint, okay, because local area network will be having limited number of users. So, there the bandwidth is not exactly a restriction. So, that is why the deteriorated payload efficiency won't matter to us much, and individually all these individual LAN segments would be having like this, means there will be header information, IP component, UDP component, RTP component, and then the payload which will go into the RTP, okay, like that for every channel.
Sir?
Yes, please.
Sir, can we have a larger payload size in this case, or do we have a larger payload size in this case?
No, individually when we are talking of the LAN segments, there the payload efficiency is poor. Okay. That means to say that the payload could be still one frame. Okay. The payload could be still one audio frame, okay, and which means to say that you may have efficiency in the range of 0.2 to 0.5. Okay. So, here we are not increasing the efficiency, rather we do not want to increase the efficiency, because here plenty of bandwidth is available. The availability of bandwidth is abundant in the individual LAN segment. So, there we are not concerned, but what we are concerned with is that when we go out of this multiplexer, okay, and then we are in the WAN segment, wide area network. There in the wide area network we are going to face some bandwidth constraint. So, now that we have decided to use a multiplexer over here, okay, what we can logically think is that why do not we take all these individual packets, okay, and then embed them together in the form of one bit stream, but then again that combined packet or that mega packet if we call, okay, that mega packet has to be transmitted over the WAN, and again it is to be transmitted over the IP and UDP. So, that means to say that what we are thinking of now is that there will be IP header, UDP header, and then this individual packets, but this individual packets coming from the different sources will also be having their own header. So, as such, if we are talking of the efficiency, we are not improving the efficiency yet till the time we achieve something like a compression in the header. Now, can we achieve that? That is what we are going to examine. So, here what we are typically having is that, supposing this is the total composition of the WAN packet, okay, and here we will be having the header as the IP plus UDP plus we are having the total information here. That means to say that the header which was already there, okay, and then the payload information. Now, out of that the IP and the UDP header, okay, we may dispense with, because what happens that this IP and UDP header will be pertaining to the source, and you can that time use this as the destination. So, from the individual source, supposing this is source S1, this is S2, S3 and up to Sn, we consider n number of sources. Now, whenever we are considering S1, the destination is this multiplexer. Now, S1 to, so the source information, destination information and the stream ID information, whatever information goes into the IP header, okay, everything has been taken care by this multiplexer. So, the multiplexer has rather identified that stream, and now the multiplexer is putting into the combined bit stream. But even in the combined bit stream also, although the IP and UDP headers for individual streams will no longer be needed, but still whenever it is multiplexing the different streams, in that case corresponding to the individual streams there must be some header, because when it is multiplexing it must identify that whether it is coming from source S1 or whether it is coming from source S2, at least some amount of information should be there. And not only that, the time stamp which will correspond to this, because if it is an audio packet that is coming from the stream S1, in that case that is associated with some time stamp information. Okay. It is also containing the destination information. So, the source information, the final end destination information and and the timestamp. So, these things will still be needed. So, there will be some header which will be anyway required. So, what we can see is that header information may be less as compared to the total header information what we have over here. So, here the IP plus UDP plus RTP, these header components, if it takes 40 bytes, maybe that now after multiplexing the individual streams what we are sending in the form of multiplexed packet, that may not contain 40 bytes, there we may be able to reduce the header size very significantly. In fact, by research it was shown that it may be reduced, the header size could be reduced to as low as 2 bytes even. So, from 40 bytes, so there is something called as the header compression. So, we are going to study that what kind of header compression scheme can we adopt, but definitely if the header compressions are done, in that case what we are considering is that for the individual streams we will consider, we will have a mini header. Okay. That mini header may be as low as 2 bytes. Okay. Mini header plus the payload, the individual stream payload. Okay. And since we are having n number of such sources, okay, it will be mini header plus payload multiplied by n. Okay. So, this will be what follows the IP and UDP, right. So, the data sequence will be first the IP header for WAN, UDP header for WAN, then mini header along with the payload for the first stream, mini header plus payload for the second stream, and so on up to n number of streams it will be there. Now, at the destination end, okay, just the reversal will be done. That means to say that here we have to have a demultiplexer. Now, what the demultiplexer will do is that the demultiplexer will identify, see, from the header information it will identify that this is the demultiplexer that we are looking for, and then after this the IP and the and after this the individual streams will be obtained. Okay. And there from the mini header information we should be able to again compose that what the desired information will be, because mini header may contain some information in the compressed form. So, there we have to again decompress it and then send it to the different receivers. So, we will be having likewise n number of receivers. Okay. So, let us say that these are R1, R2, R3 up to Rn. So, there are n number of receivers. Okay. And to each of these receivers the data packets or rather the voice packets will go, okay, with its own IP plus UDP plus RTP. Okay. So, then again to this individual LAN segments we have to form this IP UDP RTP header plus the payload information, and this will go to the different receivers at the destination end. So, where we want to have a big saving is that if a significant amount of header compression could be done while transmitting the information through the wide area network, then the overall payload efficiency can be increased. Okay. Now, what philosophy is actually adopted in order to achieve such kind of a bandwidth compression, such kind of a header compression? Now, what are the header information that will be needed? Okay. Now, when the packets are transmitted from the source to the mux, okay, the mux acting as the destination, okay, as the first destination for the source packets. Okay, it is going from just from the source to the multiplexer. Okay. The fields in the UDP that do not need to be considered are fields in the UDP IP header which do not need to be considered. These are the source IP, then the port number IP, then the port number, then the IP packet ID, and then the UDP checksum. Okay. But whenever we are recomposing, I mean at the multiplexer end, whenever we are obtaining each of these, okay, in that case the question is that what are the other information that we will be able to compress, okay, that part we see. Okay. Before that we go into one important aspect, and that is to say that at what rate are we going to deliver the packets. Okay. Let us say that supposing that there are n number of sources and all the sources they start collecting their information from this time. So, the time axis in this case we take like this, and supposing this is where the stream number 1 completes the first audio packet. Okay. Supposing the stream number 2 completes the first audio packet here, supposing the stream number 3 that takes a longer time to compose an audio packet. Okay. Supposing stream number 4 takes this much. Okay. Supposing we just consider four sources 1, 2, 3 and 4, and this is the time when its individual audio frames are ready. Now, the time at which the audio frames are getting ready, they are different, okay, and they could be different. Why? Because each source could use a different compression scheme. One of them may be using G.728, another may be using G.729. Their bit rates could be different, okay, and not only that, the amount of compression that can vary from one frame to the next, and that is why there is no guarantee that all the, I mean in fact in general it will never happen that all the channels, okay, will complete their collection of one audio frame at the same time simultaneously. Okay. So, now the question is that if such is the case, in that case what should be the rate at which we compose the packets. Okay. Do we wait till the maximum time elapses? That means to say that if we think that at this time, since at this time instant already we will be having the streams from frame number streams from 1, 2, 3 and 4, one audio frame each has arrived. So, now it is the time to send a multiplexed packet. Okay. Is it a good policy? Definitely not. Why? Because if we consider this way, then by this time, okay, we may be receiving some more packets from this. Okay. By then maybe 3 packets of 2 will be over. I mean 3 not packets, sorry, 3 frames of source 2 may be available. 2 audio frames from source 1 may be available. Okay. Maybe 1.5 times the source 4 are available, 1.5 frame time is available from source 4. So, that means to say that we should try to make optimal use. So, the policy should not be to see that which is the maximum time for one audio frame, okay, rather to say we consider that amongst the different channels which we are multiplexing, okay, which is the minimum audio frame time. Okay. Supposing Ki is the audio frame time for the ith channel. Okay. Then we should see that what is the minimum of this Ki. Now, in this case, in this particular example, when we consider this time instant, then audio frame 2 is ready, but audio frame 1 is partly ready, audio frame 3 is partly ready, 4 is also partly ready. But what we can do is that still whatever we have received from the source 1, source 3 and source 4, this information we can transmit into the packet even though they are not corresponding to one complete audio frame. It is only a part of the audio frame, but who says that we have to form one complete audio frame? It is not needed. So, if we take the frame rather to say that if the multiplexer sends out a multiplexed packet every t milliseconds. So, t is the rate at which the multiplexed packets are sent. So, this t we are measuring in milliseconds, that means to say that how many milliseconds do we take to send the multiplexed packets. Okay. So, in that case what we should achieve is that t should be less than or equal to minimum of k I. Okay. If we take the minimum of k I, this is what we have taken as minimum of k I. Alternatively, we could have accumulated the packet here itself, because even here also I mean if we take t to be only this much, in that case we are not waiting one audio frame to be completed for every channel. Okay. But nevertheless, okay, we collect this much for frame from source 1, this much from source 2, this much from source 3, this much from source 4. So, individual headers we append and we send the information. Okay. And together then we are multiplexing, and then we will be having the accumulated effects of all these bit streams, okay, accumulated effects of all these bits which will go into the multiplex bit stream. Okay. Now, so that is how the rate at which the multiplexed packets are sent is decided, that is based on the minimum of k I. Okay. Now, we again address the question of this header compression, okay, that how the header compression can be actually achieved, and there we make use of an algorithm which was suggested in 1998. In fact, the reference to that is, I am giving you the reference, that is by Kastner and Jacobson. Okay, so, this is Kastner and V. Jacobson, and the title of the paper is compressing compressing IP, UDP, RTP headers for low speed serial links. Actually, it is available as an IETF document. So, this appeared in the proceedings of IETF RFC 2508 February 1999. Okay. So, this is the compression scheme, and in fact, the paper that you can refer to learn details about this details about the multiplexing scheme, because the paper which I am referring to, they also suggested and improved upon Kastner's algorithm, and this paper is by H.P. Zhe, S.C. Liu, J.Y.B. Lee and Danny C.S. Yip. The title of the paper is A Multiplexing Scheme for H.323 voice over IP applications. And this paper appeared in IEEE journal on selected areas in communications, volume 20, number 7, September 2002. Page numbers are 1360 to 1368. Okay. So, you can have a reference to both this, okay, to understand details about this scheme. Now, yes, I was trying to tell you about the basic philosophy behind the header compression. Now, Kastner's algorithm basically takes advantage of two properties in most types of the RTP streams. And what are these? These are that most of the fields in the IP, UDP and RTP headers, they do not change over the lifetime of a session. Okay, means for a particular session they remain the same. So, naturally you are, see, whenever you are thinking of doing any header compression, you are looking for the redundant information that is present in header. Now, if you find that supposing there are 10 sources and there are 10 destinations. Okay. Now, source number 1 is sending some packets to source number 5. So, source number 1 and destination number 5, supposing they are involved in a session. Now, when source 1 is sending to destination 5 and that is declared as a session, then whatever packet source 1 is sending for that particular session, those packets will be having a set of headers. Okay. I mean, those packets will be having some header which will be there for every packet that source 1 sends to the destination. But mind you, we cannot dispense with that packet altogether, because I mean, when source 1 to destination 5 packet is identified, after that immediately source 2 may be sending the next packet to destination number 4, source 3 may be sending to destination number 10, like that different things will be there, different packets will be there, or the different streams will be formed. So, that is why we have to have some mechanism of identifying also, but that identification, is it essential for us to have the complete header information? No. So, what is being done is that, I mean, they have suggested that using a context table is, if it is possible to refer to that table and get only some identifier information, or to form only some identification information which can go into a mini header. So, rather than giving the complete header information, that means to say the constant fields which are associated with the header, that may be dispensed with, and instead of sending the constant headers, we can try to have some mini headers which will have only the changed information, okay, and through which one can identify that who is the source and who is the destination. So, there should be a reference, I mean, there should be a table, and the minimum information that will be required to refer to that table, only that will go into the mini header. I will show you this with some example. So, then it will be clear. So, the first property for most of the RTP stream is that most of the fields in the IP, UDP and RTP headers do not change over the lifetime of an RTP session. So, naturally this constant fields may be replaced with a fewer number of bits. Okay. So, the constant fields may be replaced by smaller number of bits in the mini header. Now, everything is not constant, because even though source 1 is sending the packets to destination number 5, okay, the packet is identified with some packet ID. Okay. I mean, that means to say that some kind of a sequence number will be there, because with every packet switching, as you know, that there has to be some packet ID, because there is no guarantee that the packets will be delivered exactly one after the other. In fact, individually the packets may be differently routed also, and it is only at the destination where, after identifying the packet ID, okay, the destination will put the packets in the sequence and then form the ultimate I mean information can be obtained. I mean, that happens with every packet switching scheme. So, some packet ID will be there, but when it is being generated from the source, the packet IDs which are going, or the sequence numbers which are going, that should be just incremented by 1. If the previous sequence number was 5, then the next packet will have a sequence number of 6, the next packet will have a sequence number of 7, like that. So, that is why, I mean, we need not have to send the absolute information, or rather only the incremental information, that there is an incrementing by 1, or if incrementing by 1 is implied, then we can automatically infer that in the next packet that is coming from this source to this particular destination, there one can have one number. I mean we can indicate this varying thing by having a kind of a priori knowledge that, okay, the sequence number is going to increase by 1. And likewise for the timestamp also, that the timestamp which is associated at this moment, okay, for the next packet, the timestamp, because the rate at which the packets are composed, that rate is not varying, that rate is maintained as the same. So, and the packets are also not arriving in burst. In most of the cases, we will be finding that the timestamps are also regularly updating. That means to say that there is a I mean the sequence number and timestamps, they are actually increased by some constant amounts. So, that is the second property, that RTP header fields like sequence number and timestamp are increased by a constant amount for successive packets. For successive packets in a stream. Now, when I say packets in a stream, I mean to say the same source ID and the same destination ID. Okay. Means if it is source 1 sending to destination 5, after that I mean in the multiplex we may be having source 2 sending to 6, 3 sending to 2, 4 sending to 10, like that it can happen. But again whenever I am having the next packet that source 1 sends to destination number 5, okay, then we will be having its sequence number and timestamp which are augmented by a constant factor. And if the updating of the sequence number and timestamp are there by a constant amount, in that case some kind of a differential coding can be employed to compress these fields into fewer number of bits. So, these two properties of the headers, okay, definitely leads to some amount of compression. Now, whenever we do the compression, as I was telling you that we can do the compression, but at the same time we should not be losing the identification scheme. I mean still we should be able to identify any time that okay, this part of the stream is corresponding to this source and this destination, and this would be the sequence number for that. Now, to do that we maintain a table and we will refer to the context in the tables in order to achieve that compression. So, first of all that we have a channel table, okay. We have a channel table in the multiplexer and the demultiplexer, and what is the format of that channel table? We will be having a channel identifier. So, there will be a channel ID, okay. There will be the IP address for the mux, there will be an IP address for the demultiplexing, and there will be the port address for the demultiplexing. So, demux port. You see that one multiplexer may cater to different demultiplexers, okay. There is no problem, because the scheme which I was telling you, who says that there has to be only one demux, we may have another demux, we may have another demux, like this, okay. And not only that, I mean the port address of the demux, that also could be different. So, the multiplexers IP, demultiplexers IP, demux port, everything together will define a channel, okay, because the channel is from the source to the ultimate destination, which is connected to one of the demultiplexer ports. So, if you explicitly specify that what is the mux IP, what is the demux IP, and what is the demux port, and you also give the channel identifier, then that defines a complete channel which will be there in the channel table. So, like this I mean there may be several channels, okay, and each of these channels will be listed in the form of a table which we are calling as the channel table. Then other than the channel table, there will be I mean for a particular channel ID, there will be what is called as a context mapping table. So, the context mapping table for a particular channel ID in the mux would be like this. So, for a particular channel ID, we are going to have the format like this, that first will be the source information. Now, the source information will have two components, one is the IP and the other is the port address. Then there will be RTP's source identifier, that field is referred to as RTP SSRC. Okay. Then there will be a context identifier CID. So, CID's full form is the context identifier. rather to say this is a number, this is actually a 1 byte information. Okay. This is a number that is assigned to one particular stream. So, if it is source 1 sending to destination number 5, okay, that will have a unique CID. Okay. It will be assigned a particular CID, and that CID will be there. See, first of all, that when you want, when the source 1 wants to communicate with destination number 5, in that case first of all a channel is defined for that, okay, where you have to specify that from which multiplexer it is going to which demultiplexer and what is the port number that corresponds to the destination number 5. Everything should be specified in this table, and then there will be a channel ID. Now, with the help of this channel ID, we should be able to get the complete information about this. Okay. And one of the very important fields which we have to note over here is the field that is called as the CID. This is a 1 byte field and it is referred to as the context identifier. So, this context identifier, this field will remain the same for a particular session. This field will never change for a particular session. So, CID will be there, then there will be the payload type. We are not going into the details of the individual fields, okay, because these details are not within the scope of our study. Just for the sake of completion, we are just writing the different fields, active size, idle size, okay. Do not have to really bother about these fields, okay. But where we have to again note some information is that some information corresponding to the last synchronization is also necessary to be recorded in this context mapping table. Okay. By last synchronization, I mean like this, that the headers which will be associated with the individual streams, okay, there could be 3 formats for those headers. Okay. One of the header formats is what is called as the uncompressed mini header. In the case of uncompressed mini header, we will be having the sequence number. Okay, this is the context sequence, CSEQ corresponds to the context sequence. Okay. This in fact gets updated with every packet, okay, this gets updated. So, C sequence will get updated for every packet. Then there will be the CID, the context identifier which I said just now. So, this is 1 byte of information. In fact, there will be some identification information in this 4 bits, and the C sequence will be a 4 bit information, whereas CID will be 8 bit information, and followed by this there will be the full RTP header, and the full RTP header will be greater than or equal to 12 bytes. This is where the complete information will go, but this is again a mini header because we have dispensed with whatever was there in the as the constant fields in the IP UDP headers. Okay, we have eliminated that. So, this is the uncompressed form of the mini header, but we can also have some compressed form of mini header which goes like this, that in the compressed form we will be having in the first byte 4 bytes will be reserved for C sequence, the next byte will be reserved for the CID, and 6 bytes of information will be there. One is what is called as the R sequence. Now, this is the overall sequence number. Overall sequence number means the sequence number which is there in the multiplexed stream, and this is a 2 byte information, okay, and there is a timestamp which is, so RTP sequence, and this is the RTP time. So, RTP sequence is the accumulated sequence, and R time is the accumulated timestamp. Accumulated timestamp is 4 byte information. So, naturally this is some form of a compressed form, but this is called as a synchronization mini header. This is called as the synchronization mini header, and why this is called as synchronization mini header is that even if we lose synchronization, okay, using this mini header we will be able to get back that what the timestamp and what the overall sequence numbers are there, because we may miss some of the streams in between, and in that case there should not be any error that should happen in our timestamp calculation or sequence number calculation, because if we are relying only upon the CID, okay, in that case CID and C sequence, in that case there is a risk that this synchronization could be lost. So, periodically we have to send this synchronization mini header information, okay. And the third form of synchronization is the compressed form, okay. The compressed form of mini header, which is only a 2 byte information. The compressed mini header just contains the some identification that it is a compressed mini header, but there will be a context sequence number C sequence of 4 bits followed by the context identifier of 8 bits only, that is all. So, just 2 bytes of information. Normally this 2 bytes of information should be enough, because what you can do is that using this CID, okay, one can completely identify the stream by looking into the context table, okay. Now, in this class I could not give example, rather there was no time to give some example pertaining to this, but in the next class I will be taking up some specific examples, okay, and I suppose that that will make the concepts more clear, that how one can compress the header information, and then we will be talking about the performance in the multiplexed domain of H.323. Thank you.